There's for this lab, there's no formal report, so no abstract, no introduction, none of that. For this lab, all I want is a sheet that shows me what ions you found in solution. For example, these cations or these anions. But your grade isn't going to be, if you got those right entirely. Otherwise, the potential to lose a lot of points if you made some mistakes. So, in addition to that, what I want you to do is some kind of known analysis. And what that's going to involve is writing all the observations and equations for each cation, all 10 of them, not just the ones that you had. And so essentially what that is, do you know all the observations and equations I've been writing on the board? All you have to do is write those on a piece of paper and hand those in with your reports as well. Right. I don't want you to combine them. A lot of people, what they do is they say, well, I don't want to write that over again. HCl, HCl, HCl is the first step. And so they skip that. Well, if you skip it, I'm going to deduct points. So you have to show all the steps. And it's not that, it's not that many steps per ion. And so just write it down. Is that clear for the report? When is that going to be due? Okay, the due date is next week. Yes, Thursday. We have an exam on Thursday too. Does it have to be typed? No, it could be handwritten. Okay. Uh-huh.
You said so we're turning in a sheet as well as like procedures and stuff, or no? Just like
No.
observations, just your observations then, and then what you wrote on the board.
You're going to turn in a sheet that looks like this. Carbonate, step 1, observation equation, step 2. It's just that. Basically, it's so simple. This report shouldn't take you very long at all because I gave you all the observations and equations already. And so all you have to do is just write those on probably a few sheets of paper, 5 sheets of paper or something, and then turn in one sheet. For the cations, just list the cations that you found. I found sodium ion, I found this ion. That's it, just a list, and I'll check them. At one time I did it. This lab is worth a lot of points because we have so many lab periods devoted to this. And so at one time, if somebody missed one ion or something like that, then their grade suffered because it was a big hit. And so what I did was I tried to make the equations, the observations and the equations worth a significant chunk of your grade. Well, that could be good or it could be bad. Every semester there's somebody who never wrote down any of the observations or equations and didn't quite catch that. And so there you might lose points then. And so the points are going to be spread apart over these two things. Uh-huh. All right. If there are no questions, let me just briefly go over the anion analysis and write down the observations and equations for the anions. And so what's the first anion you're testing for? Sulfate? You've done the sulfate before in Chem 1A. And so this test is going to be very similar. We take our unknown, aqueous, and then add some HCl and some barium chloride, and we end up with a white precipitate. And so the equation here is if there's sulfate ions present, then those will react with barium to produce BaSO4. BaSO4 is a white PPT. And so the question comes, why HCl? Why are you adding HCl to this? You remember this from 1A, Uthma? We added the HCl there. Anthony, you remember? Why did we add HCl in the sulfate analysis? We did the same thing back in 1A. Ashley, remember that? We added the HCl to Bernice. No, nobody remembers.
Is it to join to interfering ions?
Yeah, exactly. And so we got to destroy interfering ions because not just sulfate precipitates, but phosphate will precipitate. Good. So phosphate is called an interfering ion. It's called an interfering ion because it also forms a white-looking precipitate. And so this white precipitate might be confused with barium sulfate. Carbonate is an interfering ion because barium carbonate is or looks just like barium sulfate. It's hard to tell the difference. Right? Any other interfering ions, etc. Could be others, but with HCl, you know, if you take barium sulfate with HCl, you should form barium chloride and H2SO4. You know, this is just a metathesis reaction. I'm not going to balance this, but there's a driving. Is there a driving force for this one? We're going from HCl to H2SO4. Is that a driving force? No. Strong acid to strong acid is not a driving force. So basically, there's no driving force, and we expect NR, a reaction. But if we add excess HCl to barium phosphate, we'll get barium chloride plus phosphoric acid. Here there's a driving force because we're going from a stronger acid, HCl, to a weaker acid, phosphoric. And so HCl will dissolve this precipitate. And then, of course, for carbonates, we'll get, you know, H2O liquid plus CO2 gas plus barium chloride. So we could balance those later. But the phosphate and carbonate and maybe oxalate, so somebody said oxalate this morning. I don't know if oxalate's on your list of anion unknowns. I don't think it is it? No, so we don't have to worry about it. And so these would be the primary interfering, although phosphate's not on your list either, is it? Carbonate. All right, next, what? Chloride, is that the next thing? Nitrate, okay. So let's take a look at nitrate here. This analysis for sulfate relied on the metathesis. Is it okay to erase this? Do you guys get it? You're still working on it? You didn't get it?
I got it.
You got it? All right, that was a metathesis. This is going to be a redox reaction. What are we doing with nitrate? So we take our unknown aqueous and we add ferrous sulfate. Ferrous is iron 2. This is green. Iron 2 sulfate's not so stable. It gets oxidized by air to form iron 3. And so you always look at your ferrous sulfate. If it looks green, it's good. If it looks yellow, it's gone bad. It's not going to work. And so we have our unknown plus ferrous sulfate plus what? Sulfuric acid. We're not using the dilute sulfuric acid. What concentration is dilute sulfuric acid? Dilute sulfuric acid is considered 6 molar. That's dilute. We're going to use the concentrated stuff, which is double-digit molarity. You know, it's 18 molars. And so we got to be careful with this stuff. What we should observe here is the brown ring, they call it. This is the brown ring test. It's not really a ring. Sometimes it looks like a ring because the test tube. And so what's the reaction here? Well, the brown ring, let's take a look at the equations. And so our unknown is going to contain nitrate. And it's going to contain some acid. And so nitrate with acid, this is the half reaction that we get from our book. It goes to NO gas plus 2 H2O liquids. And so nitrate and acid is a pretty good oxidizer, and iron 2 is a good reducer. You know, iron 2 is not stable in air. You know, air is plenty powerful enough to oxidize it to iron 3. Well, if we got nitric acid, for sure that's going to oxidize the iron 2 rapidly to iron 3. And so the half reaction for this goes to iron 3 plus an electron. And so we need 3 iron 2s to generate 3 electrons, and we have 3 electrons being consumed by the nitric acid. And so the net reaction for this is nitrate plus 4H plus 3 Fe2 plus goes to NO gas plus 2 H2O liquid plus 3 Fe3 plus. Well, the problem is nitrate's colorless, but so is NO. NO is a CCG. It's a clear colorless gas. And so where does the brown color come from? The brown color doesn't come from iron 3. You'll see the green color disappear. It should be replaced with a more yellow color. But that, you know, that really doesn't mean that we have nitrate present. We could have some other oxidizing agent present. And so what we want to do is we want to be able to detect the presence of NO. And there's a way we can do it, because NO goes by different names. It's called nitrogen monoxide. It's also called nitric oxide, and it's also called, NO is also called nitrocil. Nitrocil is the name we give it when it's used as a ligand. Well, we need some central metal that it can bind to. So is the NO going to bind to, well, it can bind to iron 3, but does it bind to iron 3? No, it's going to bind to iron 2. And so we need excess iron 2 here, because we need to form this complex. It's going to be iron 2 plus a nitrocil, and that's going to give us FeNO 2 plus. And this is brown. This is aqueous. And so how do we detect this? The way we detect this is going to be like this. We have to be very careful here because we are using concentrated sulfuric acid. Concentrated sulfuric acid is very dangerous. It generates a lot of heat. And so do not hold the test tube with your fingers. We use a test tube clamp to hold the test tube because it gets very hot. In fact, if you add it too quickly, the solution can start to boil and splatter. In fact, did I tell you one of my students got a 3rd-degree burn? Yeah. This is how she got it. She dumped in the concentrated sulfuric acid all at once. It superheated the water and started splattering, and some concentrated sulfuric acid shot out and landed on her arm. Just a tiny drop, but it caused some charring of the skin. And so watch out here. And so the way we're going to do this is we're going to hold the test tube with a test tube clamp. And then down here, we're going to have our solution. The solution is going to consist of nitrate and ferrous sulfate. And so we just need the iron. Sulfate turns out to be a spectator here. And then sulfuric acid is like a syrup, a viscous syrup. And so as you drop it, the sulfuric acid into the test tube, what you want it to do is you want it to hit the inside wall of the test tube and then just slowly flow down the side. And what's going to happen is the sulfuric acid doesn't mix initially, it just sinks to the bottom of the test tube. And that's exactly what we want to happen. We don't want the sulfuric acid to mix with the water as much as possible. We want to create two layers. We want to create a layer of concentrated sulfuric acid at the bottom of the test tube. Now, at the interface between the concentrated sulfuric acid and the nitrate and iron 2 solution, this is where we should detect the brown ring, right here. Just a small layer of brown solution. So be careful with this one because it's dangerous. All right, what's the next ion we're testing for? Okay, chloride. Chloride is kind of the opposite, or actually it's the same as the silver test, right? Chloride and silver, they like each other. And so if we have an unknown aqueous and we add silver nitrate, did I tell you about my student who had an important job interview? Did I tell you about her? It was during our anion analysis, and she came up to me at the end of the lab and said, I've been washing my hands for 30 minutes, but I cannot wash the black stains off my hand. It just won't come off, even with lots of soap. It turns out it's silver nitrate stains your skin black, and it takes a week at least to come off. And so she was very upset because she had an important job interview right after class, and her hands had black stains all over them. So be careful with this. Okay, but what we expect here is a white PPT. We've seen this reaction before. It's just chloride and silver ions combining to form silver chloride. In the silver analysis, we dissolved this precipitate using ammonia and then recrystallized or reprecipitated it using nitric acid. Are we going to do the same thing? No. And so, actually, we're just going to leave it like this. But the problem is this unknown has to be known not to contain certain things. For example, this unknown better not contain bromide, because if this unknown contains bromide, we could get a precipitate here as well, right? The silver bromide has a slight yellow color to it, but it's still hard to tell. It shouldn't have any carbonate. Well, carbonate's no problem, because if we precipitate out silver carbonate, we could kill that with acid. Whereas silver chloride won't dissolve in acid because we just form strong acid to strong acid. And so this will be the light version of this. So if we know that our unknown doesn't have certain things, then we end the test here. If our unknown could potentially have those, then we do subsequent confirmatory tests to make sure that it was indeed chloride. All right, what's next? Bromide. Is it okay to erase that? Let me know. Bromide, you've done this test before in Chem 1A, experiment 18. Have you done it? And that is, we take our unknown and we mix that with chlorine water. That is just an aqueous solution of chlorine. And then we add, in Chem 1A we added chloroform, but in Chem 1B we're going to add mineral oil. In Chem 1A, the chloroform was more dense than water, and chloroform and water don't mix. So the chloroform sunk to the bottom. Mineral oil is less dense than water, so mineral oil will float on the top of water. And then what we're going to do is we're going to do an extraction. So what we're going to get is a orange mineral oil there. Orange. It's a red-orange color. And so the reaction is like this. If we have bromide present, the bromide will be oxidized by the chlorine to bromine, and the chloride will be reduced to chloride. Bromine in water, this is aqueous, bromine in water is faint orange. But what we're going to do is we're going to try to concentrate the bromine in a small amount of mineral oil. Don't add too much mineral oil, otherwise the color is going to be weak. You just want a little bit of mineral oil. And we're going to do a process called solvent extraction. In solvent extraction, we extract the solute from one solvent, the solute being bromine, in the solvent being water. We extract the solute from one solvent into another solvent. The other solvent will be mineral oil. And bromine prefers to be dissolved in mineral oil because bromine is nonpolar, mineral oil is nonpolar, and like dissolves like. And so what we should be able to do is we should be able to concentrate this so that the color really stands out. And so we should get a bright red-orange here. This works well. The chlorine water should have a yellow color to it, but our chlorine water is very weak and it almost looks colorless. And so that means you might have to add a lot of bromide to get this to work. All right, so what you're going to do is you're going to stopper the test tube and then shake it to get little droplets of mineral oil to mix, to form some kind of emulsion with water, and then the mineral oil will extract the bromine out of the water layer. Okay, so just stopper it and shake it. All right, after bromide comes iodide. And so iodide can be oxidized by chlorine water to form iodine. Iodine in water is a faint purple color. What we want to do is we want to extract the iodine from the water layer into the mineral oil layer and then concentrate it. And so don't add too much mineral oil again, so that we get a bright purple mineral oil layer. Okay, what's next? Carbonate. We'll do it over here. Carbonate, if our unknown contains carbonate, and we add, we're adding sulfuric acid. Are we adding sulfuric acid? Yeah, a lot of people prefer to add hydrochloric acid at this point. Do you know why? Chloride reacts with fewer things than sulfate. Sulfate is more reactive. And some people prefer nitric acid because in metathesis reactions, nitrate's unreactive. Schism redox reactions, nitrate's quite reactive. But it's okay, we're going to follow the procedure. So we're going to get unknown plus H2SO4, but this, sulfate can cause other reactions to occur. And this is going to generate a CCG, clear colorless gas. And so the reaction here is just carbonate That's the sulfuric acid. This is going to yield H2O liquid plus CO2 gas plus plus sulfate. Okay, then the final thing is to confirm, is that gas really CO2? Is there a way to tell if that gas is CO2 or not? There is. And this is why our barium hydroxide always looks contaminated. Our barium hydroxide always looks contaminated because it reacts with CO2 gas and air and forms barium carbonate. And so when you use that barium hydroxide, use it centrifuge it and just use the liquid on the top. And so we're going to take the CCG from step 1 and then react it with some barium hydroxide, and we get a white PPT. And so the CO2 gas reacts with aqueous barium hydroxide, and we form barium carbonate, solid, plus H2O liquid. This reaction is what type of reaction? Here. What kind? This is an acid-base. What kind of acid-base reaction is it? All acid-base reactions are neutralization. And so what type? Is it a Bronsted, Lewis? What is it? Arrhenius? It's not Arrhenius. There are going to be 3, Arrhenius, Bronsted, and Lewis. What is this one? Bronsted? This one's a Lewis. This is a Lewis acid-base reaction. And so we have this Lewis acid, but the way we're going to do this is kind of funny because we're going to generate the CO2 gas. So as the CO2 gas rises, you know, let's say this is the test tube, we're going to hold a dropper that has a little bit, a half drop of barium hydroxide, AQ, suspended on the end of it. And so as the CO2 gas hits the surface of that, we should see a white precipitate or white film form on the surface. But the problem is if you hold that in the lab and just exhale on it, you're going to see the same thing, right? Or if you hold it and you don't exhale, you'll still see it. It'll just take longer to develop because there's CO2 present naturally in air. And so we have to be careful that we just let the gas that's being generated here hit that, and we want to see it rapidly develop. That would be a positive test for carbonate. All right, what's the next ion? Is that it? All right. Okay, so that's it. Make sure you turn in your report. I'll be right back.
Oh, we didn't
Go under. Yeah. Well, I did the last one, but we didn't do it.